Hello. Can you hear me? Yes, you can hear me. Okay. Thank you for inviting me to this conference. Oh, now it works. Okay. I would like to tell you about one simple thing which can be quite helpful in creating good test ideas in general. That's the whole point of my presentation. And this technique is called TQED. I will explain later why, where does it come from. And I will also show you some experimental work which was done on this model to experimentally verify that it really works. First, motivation. Why? Why this thing? Why this model? I don't know what are your experiences, but my experience is that when I read some books, when I read some articles, when I go to conferences, when I read some blog posts and so on, I see that what draws the tester's attention most are these things here. It's about test management, test organization, test process, test planning, this kind of stuff. But I have this feeling that it's not really, people don't really talk about testing. That's my impression. I mean, when I started my journey with software testing, I knew nothing. And my first question was, when I started to study some things about this testing, okay, I know there are these test phases, there's test management, we need to plan these tests and so on and so on. But finally, I need to write this test case, to design it, to create it somehow. So how should I do this? Where does it come from? How can I do this? And I couldn't find an answer for this. And then later, when I had some experience, I realized that it's because it's difficult. All these test ideas that we design must be, on one hand, very concrete, and on the other, they depend on context, so they differ across projects. You cannot apply one concrete technique to all your projects. So that's why people write a lot about testing, but they don't write much about new test techniques. We don't see any, I don't know, every single week a new test technique which appears and everyone can use it. So that's first thing. Now the question is, okay, it's difficult, but maybe we should try it. We know there are many test techniques. We know a lot of them. So, but they have some drawbacks. They have some caveats. So maybe we could try to find a technique which will be very concrete and very universal at the same time. It seems difficult, but I think that at least we can try and see what happens. So can we generalize this test approach? Yes, we can. Of course, we don't do this often because, as I said, it's quite difficult. But we should, because it's always nice to have a universal tool which helps us at least to boost our creativity in creating these good, strong test cases that have great probability in detecting any defects and bugs. And we can use models for this task. So what is a model? This is a boring definition from some, I don't know even where did I take it, but we will work on this definition. We'll change it slightly later. So what is a model? A model is an abstract representation of something in general, and it's used to describe and explain phenomena that cannot be experienced directly. And they are mentally visual way of linking theory with experiment, and they guide research by being simplified representations of an imagined reality that enable predictions to be developed and tested by experiment. It's a very scientific method. It's a model that comes from scientific theory, methodology of science. But we can take it and modify it for our purposes. So what is a model for us? So we would like to have a model which represents our software, that can be used to describe and explain bugs, because that's what we are paid for. That cannot be experienced directly, which is quite a trivial and obvious thing. And we want them to be this visual way of linking development with execution, so that they guide us by being simplified representations of this reality that enable bug ideas to be detected. That's our goal. This is a model for us. That's how we should understand a model when we want to create one of these models. So a good model should have some features, some characteristics. So here we can see a model of this Iron Throne from Game of Thrones. It looks like the real one, and it may allow us to say something about this real Iron Throne. Of course, this is a stupid example, but the idea is here on the left. So the model should model the problem domain correctly, so it should be a proper model for this given particular thing we are working on. It should be simple. Of course, we can say that the reality that we work with is a model. It's the best model of reality, the reality itself, but it's completely useless for us, for our scientific or software testing purposes. It should be understandable so that all people who use it in practice should know it, and it should speak the right language, this, let's say, business domain language. It should be flexible and generic. This is the biggest problem with software test techniques, because most of them, if they, this is this trade-off. If they are very concrete, they guide us really well in designing tests. They are very restricted in the area of their application. And if they are very general, they don't really help us. They don't provide a concrete, detailed way of thinking about this, inventing these test ideas. So it should be flexible. It should be generic. Also should be able to make predictions. That's the scientific part of this, and it's maybe not so important for us. Actually, we could say that it should make predictions in a way that a good model should tell us where should we find a bug. That's this predictive feature, predictive characteristic of a good model. So I will tell you in a few slides about this model, TQED, and the question is, okay, we can think about any kind of model we want, but does it work? Does it really work? There are a plethora of models. For example, in reliability theory, there's maybe this is you are the most familiar with IT. So there's this area called reliability theory, and there are like gazillions models of reliability of software reliability. But the truth is that maybe one or two of them were verified in practice, and the whole rest is just a theory, never verified experimentally. So that's just a pure theoretical thing. So we would like to know, if we provide some new method to design our tests, does it really help us? Is it useful for us? So we will do this through this scientific approach. So I will show you the experiment which verifies this model accuracy. And also I will tell you about one practical application of this thing, but unfortunately due to some things I cannot tell you much, but it will be written on one of the slides later. So the inspiration for this approach to this TQED model comes from physics. Physics deals with reality. Reality is complicated, but physics has some tools to describe this reality. And these tools are quite simple in the sense of their complexity. Of course, physics is not simple as the science, but the tools are simple when we compare them to this very, very complicated reality we live in. So physics operates with a few characteristics like mass, energy, temperature, this kind of stuff that are used to describe any possible situation that we can meet in the real world, both in micro level, macro level, normal level, everywhere. So when we imagine this simple example of a volcano, we can describe this phenomenon in terms of some quantities. So we have a lot of ashes, for example. In terms of some events, something happens, there's this eruption. In terms of data, there is some matter, for example, this lava. And there is some time aspect. This whole process goes in time, so this lava solidifies, for example. And we can notice that we can use these four simple, let's say, dimensions of reality. We can apply them directly to as the dimensions of software. So when we consider, for example, a source code, it can be a black box testing of any application, or it can be source code, anything. We can also say that, for example, we have some values. So these are quantities. We have some events invoking some function, adding something, substituting something, invoking this function, returning something. These are all events. These are things that happen. We have some data, which are, for example, variables here in this example. And we have time, which can be understood as the sequence of executing these instructions. So these are four basic, let's call them dimensions, that enable us to describe practically any kind of software on any level of abstraction we want. So this data can be a variable, but this data can be an electronic impulse or a bit or something very high level, like, I don't know, some document in which this application generates, for example. So this analogy is this. Data will be like matter, events will be like thermodynamics, quantity like the amount of substance, and time is just good old time. So if we can describe any physical phenomenon as a combination of basic physical terms, then using this transformation, we can also do this for software in terms of these basic software dimensions. And that's the whole idea, the inspiration for this very simple tool. And this tool, it really is this. This is the model, the picture of this model. It operates on, it says that any software any phenomenon, any aspect, any part of the software can be described in terms of one of these things, or, that's the most interesting thing, it can be described as a combination of some of them. For example, we can describe some phenomenon as a combination of some data and some aspect of time. These three dots mean like that we can create these combinations more and more complicated, so we can involve three of these dimensions, 4, 5, and so on and so on. So, for example, we can model something as the combination of one data with another data, with one event, with some quantity, and with some time, for example. This may be probably some very complicated event. So that's the model. And we can relate these concrete characteristics, aspects of software to these model dimensions. For example, data can be any input, it can be a cookie, it can be a file name, some string, it can be configuration item, a document, things like that. Events, it may be defining a variable, clicking something in application, some arrival of a message, invoking some method, and so on. This is something that happens. That's the event. Time can be related with any time dependencies, the notion of succession, or the notion of parallelism, the notion of sequencing, repeating, persistence, anything that we can imagine that is related to time. And quantity can be, for example, understood as something that is empty, so 0 elements of something, something that is unique, something that is minimal or maximal, or just below minimum, or just above maximum, or a typical value or something like that. The important thing is here that it's not these are just examples, so it's the tester who decides what should be understood at which dimension, because this model does not tell you exactly what should you connect with a given dimension. That's on your side. And now, so this is a very theoretical, very dry, I would say, thing. But now I would like to present you 3 simple examples of how you can use this model in practice. These 2 examples will be very simple, very artificial, but the point is to show you some important features that this model gives the tester. The practical one will be the practical application in a simple application. It will be Google Calendar. I will show you a bug in Google Calendar. So imagine that we need to test this ticket machine. We can insert there some coins, some notes. It accepts these 5 cents, 10 cents, and so on. For some amounts, 760 or more, it accepts also these notes. And we can, when we click this button, we will increase by 1 the number of tickets we want to buy. The maximal number of tickets is 10. There are some simple requirements for this, and we are going to test it. I would like to distinguish between let's say boring testing and creative testing. By boring testing, I mean the major part of the tester's work usually, because the tester gets the requirements and needs to create these tests one by one, exactly deriving them exactly from these requirements. Sometimes it can be boring. There's much more fun when we can do this testing on our own, when we can use our imagination, our creativeness, this kind of stuff. So this model works in both situations, but it's more fun to use it in the other one. So I will focus on this other one. So how can we join these or relate the entities from this business domain to these dimensions in the model? For example, a ticket is an object, it's kind of a data. A coin or banknote is a data. Total price, it's a number, it's a data, and so on. Events, what can happen in this application? We can press some button. This machine can give us a change. We can insert something, a coin or banknote, in this this thing here. Oh, sorry. We can do something for a long time or short time, or do something in parallel. Like, for example, we can push 2 buttons at the same time. And quantity, no, well, we can have high price, low price, high number of coins, low number of coins, this kind of stuff. So that's the first step. We can combine, we can relate entities, real business domain entities, to these dimensions. And then we can use this approach that allows us to boost our creativity, to generate some nice test ideas by combining these dimensions and looking at what's the result and what's the interpretation of this combination in the real world. So the first example is a very simple example which shows you how to just to create some test idea. We can select one dimension, let it be denomination, let it be a quantity, let it be boundary value, and data, the total price. Let's say we choose these 3 dimensions, concrete dimensions. And when we think about this denomination and boundary value, we can think about what these 2 things have in common. Does it make sense to consider them as a combination? Denomination and boundary value. Well, one of the possible interpretations may be that we can use coins with minimal denomination. So we can take this 5 cents or 10 groszy in Poland or something like that. So that may be some idea to check, or it may be some partial idea which can be used later for some other ideas. Then when we take this quantity and the second data, boundary value and total price, we can think about maximal possible price, so that we can buy something for maximal possible price in this ticket machine. And then we can combine these two things, use coins with minimal denomination and buy for the maximal possible price. And when you combine it in a natural way, we see that a test idea arrives to our mind, that we can try to buy as much as possible for as small amounts of denomination of coins as possible. And I wouldn't call myself a tester if I didn't try this in practice. So I did this. When I was riding once a bus, we in Krakow have these ticket machines in buses. I took this 10 groszy, like really a lot of 10 groszy coins, and I went to this machine and I bought just one ticket. It wasn't even the maximal possible price, but it was for like 4 zł or something, so it was I had to use a lot of coins for this. And I started inserting these coins one by one. Every step I did was according to the requirements, because I could use 10 groszy, I could buy a ticket, so I was entering these coins to this machine. It took me a long time, of course. There were some other people waiting, so it was quite a dangerous test for me. And the test failed because I had like 2 coins left, and this machine, like it canceled this operation by itself. It decided that this operation is cancelled, so it started to throw these coins to this dispenser. I just looked at these people and I just then insert 5 zł or something, so that not to be killed by these people. And the thing is now, why it happened? Why did it happen? There may be at least 2 reasons. First one is that it took a too long time. Maybe there's some period of time that this operation should fit in, or maybe this thing to which we insert coins does not have enough room for such a lot of number of coins. These are 2 possible reasons that came up to my mind. I don't know if any of them was the real one, but anyway, the test failed. I just discovered something interesting about this ticket machine. So that's the first example, how to create these ideas. Another interesting thing is that using such an approach can allow us to rethink some things related to design, to application design. For example, when we consider pressing a button and a quantity which is a lot of, we can combine them to an idea buying a lot of tickets. Then we have this event cancel, and we have this time dimension, a long process. So we can combine this buying a lot of tickets with cancel operation, which means that we should repeat the whole process again. And then if this process takes us really a lot of time, then the question now is, because there was this cancel button in this machine, maybe you remember that. So in this situation, how should we define cancel operation in this machine? Should it cancel only the last ticket or the whole business process that was undertaken by the buyer, by the client who buys the ticket? So this issue is about system design, because it allows us to think about how should we, which way would be better for users, for example. That's the simplest interpretation of this thing. So that's the second example, an emergent design by analyzing these combinations of different dimensions. And the third thing is the practical application of this technique. You probably all know Google Calendar, right? All of you know how does it work, yes? Yes, okay. So it's, unfortunately, I forgot to translate it. It's in Polish, but it's not a problem. So we just, when we want to create an event, we just put here a title of this event and maybe a date or the hour. We can add some particular date here, and then we can save this event to our calendar. So suppose we have data. It's natural to consider event name as a data and this hour as data, because it really comes directly from the way that application looks, that from the interface. It's like this interface is kind of some form of pseudo requirements, I would say, in this sense. So we can take these dimensions and event, because there's this button save, create the event, and we can think about this process. When we combine event name with hour, then we have data combination, name that contains hour, that's quite obvious. When we have hour and quantity, which is like a part of something, then we can have this idea that this hour contains numbers. And when you combine these two with quantity more than one, we can imagine, it's the creative part of this whole process, we can imagine the situation that we have in the string, which has this title of the event, we have this event name, we have this hour, and we have some other number in this string. And then we can create such an event and see what happens. Have you tried this at home? No. So when you do this, it may look like this. If I write in this title, a meeting in a room 121 at 12:30, and save this, it will create this event at hour 1:21. Because it probably interprets this thing as an hour, and this is ignored. So apparently, Google, the big, great Google, all-knowing, all-powerful Google, which hires like tons of experts in IT, experts in machine learning, experts in everything, they cannot really create the application, the calendar application that correctly processes the regular expression that gives us the time from the string. Or or maybe it does, but it interprets it in a rather weird way. So we found something interesting here, at least something that can be raised to Google. That's the third simple example of how we can use this technique. Now let us compare this approach, very simple approach, with other models. First, how this model can help us in different types of our testers' tasks. When we do this boring requirement testing, we of course test these happy paths, so-called happy paths. It allows us to make this testing more systematic because we can, when we create these basic dimensions, we can create a procedure that will try to combine each of them with each other, or any other type of combining process that allows us to go through all these interesting combinations. When we want to check the user's non-intended behavior, these errors, these are like almost happy paths. It can allow us to mimic the user's, let's say, creativity in using the application. When we do this so-called dirty testing, so we try to destroy this application, so we try to use it in a really weird way. It may help us to check what can go wrong. When we validate software, it can support system thinking, this big picture of the system. Now, there is a lot of test techniques. Here are some examples. This Venn diagram has these 3 or 4 goals. For each of them, we have some sample test techniques, and we can, of course, you can argue that it should look maybe different or something, but the important thing here is that the techniques that cover all these goals, so we could say the techniques that are quite universal in testers' approach, are exploratory testing and quality models, like the ones from this ISO standards and this kind of stuff. These are, let's say, the most general approaches. But when we compare these models in terms of these two criteria, which give us kind of a trade-off, they are contradictory in a way. I mean, correctness and universality, we can see that they differ. By concreteness, I mean a degree to which a method helps us in creating a concrete idea. The best concrete model would be the one that gives us a concrete test case, the concrete sequence of actions that we should perform. Of course, such methods don't exist, but this is this ideal point in this concreteness dimension. And universality is a degree to which a method can be applied. So if I can apply this technique in just one particular type of a project with some particular type of the software, it's very low. If I can use it everywhere, it's the ideal model in terms of universality. So when we compare them, we can see that these exploratory testing, test heuristics, which are like, do you know this test heuristics by Bach or by these other guys from this context-driven school, or no? There, if you Google this test heuristics, you will find some material on that. They are quite universal, but they don't really give you a concrete idea how to test. For example, one of these heuristics is provided by Bach, James Bach, is this check each implemented function. It's quite a very nice heuristic because we should cover, have full coverage of functionality, but it doesn't really tell us how should I test this function X, for example. I don't know that. So this TQED model seems to be a little bit concrete because it operates on, it is general, but it invites the tester to define these dimensions, and then these dimensions are concrete entities taken from this business domain. So it's quite a concrete thing. In the later work. We have, of course, these formal test design techniques like this boundary value analysis and decision tables and this kind of stuff. They are very concrete, very, very, very concrete, but each of them has some specific error model behind this technique, and it can be used only in some particular type of testing. For example, state machine testing can be used only to check systems behavior. We cannot check the correctness of domain implementation, because this is done by this boundary value analysis or some domain analysis or some other kind of techniques. So there are these trade-offs, but this technique seems to be quite nice in terms of these two dimensions. So now let's see, does it really work? Or is it just a humbug? Well, let's do the controlled experiment. We performed a controlled experiment on students at the university. And the research hypothesis was that using this model increases the tester's creativity in general. Of course, there's this question, what does the tester's creativity mean? It's a difficult thing to formally define. So the experimental setup was this. We split the students into two more or less equal groups. One of them used this technique, another one did not. They were generating test ideas for two simple test problems. I will tell about them later. And there was a group of experts which received this combined list of test ideas. They did not know which test idea was created by which group. And their task was to evaluate these ideas on some scale from 1 to 4, where 1 meant it's a trivial thing, anyone can invent this, it does not really check anything, it won't detect any serious bug. To 4, which means it was very creative, very nice, there is a high chance of, high probability of detecting some weird things when we use this test idea in testing the system. So then they evaluated this, and each then the test ideas were split again to the groups, and then we compared this. We called it creativity factor. This mean value of this, or the sum of this creativity factor for all the test ideas in these both groups. The groups, as I said, were comparable in terms of these things, so it's a nice thing when you design an experiment. It's important that the groups are more or less equal, at least in terms of factors that could impact somehow on this experiment result. The two systems they had to deal with were one was the parking gate. It's a physical system. There was the task was defined in a way that the students had to put more attention on some behavioral aspect of the system, and it was user-centered. The other one, the library, was a typical software system. The main thing there was business logic to check, and it was back-end oriented. So we took these two quite different projects to see if this technique works quite well on different types of projects, on different types of testers' tasks. And the main result was this. When we calculated these mean creativity factors for per tester in each group, it turned out that for the first experiment, the TQED group had this 31 points, while the control group had 25. In the second one, the TQED had 22 compared to 17 point something for the control group. And these numbers mean that these results are statistically significant. So it means that we can reject the hypothesis that using this TQED method does not give us anything in the most general terms. That we can say it this way. So it seems it's quite a nice thing. Then we also checked the particular test ideas which were common in both groups and the ones that were only in one of these groups. So for example, for this parking gate, in total there was 86 test ideas generated. 46 of them were in both groups. At least one tester in each group invented the same test idea. There were 28 ideas that were invented only by TQED group and 12 that were invented only by the control group. And for this 46 in common, the mean creativity factor was 2.11. For these 28 unique for TQED group, it was 2.23. And for the unique for control group, it was 1.94. So we can see that it's a larger number than this one. And there's more test ideas, unique test ideas in this TQED group as well. The groups were of equal, there were equal number of participants, so we can compare these numbers. And for the other one, it was quite comparable. But the TQED group generated twice more test ideas than the control group. And they were comparable in terms of creativity factor. So it seems again that there may be something in this approach. Yeah, we can argue that using this technique creates some, or allows us to create better tests. The point is that the goal is to find these bugs, and these experts who were evaluating these test ideas, they couldn't answer this question. Does this test idea, is it able to detect these bugs? So it's problematic, of course. So there are of course threats to validity. As a scientist, I perfectly know that I cannot generalize these results to everything, to all the whole reality, because of these things. Yeah, because the groups were small. We didn't perform this experiment on like 1,000 testers. There were only 17 students in one group, 16 in the other one, and 13 experts. The participants were students, not professional testers. We couldn't really verify whether these TQED guys, because they had to acknowledge themselves with this technique at home for 1 hour. Of course, they were students, then they probably did not do this. But anyway, even if they did not do this, it's even better for us because the results show that this group is better. So even if they don't study, even if they didn't study this technique at home, they had this form which they could use during the experiment. We can say that this method is quite simple. The learning curve is very nice because they can learn this technique quickly. And of course, this notion of creativity, the most problematic one, it's quite imprecise. It's not equal to the notion of high probability of the failure detection. There was this, I call it secret case study. I wanted to, when I was preparing this talk, I wanted to tell you about this because I know about one real application in one real company, in one really test project. The project manager said to me that it really helped them, but I know only this thing, that it really helped them. I know no details. I wanted to use at least some abstract data to show you on the slide, but it was so secret that they didn't allow me to do this. So I won't spend more time for this case, although it's quite a nice thing that it was used in a real project and it helped At least it helped testers in their everyday work. You can find some more details about this thing and other things related to thinking in testing in this book. And the final takeaways here are, first, this model I have just told you about, it's not a rocket science. It's a very simple thing. It's almost trivial thing. It uses notions that are well known. Everyone knows what a data is, what an event is, and so on. The only creative part is that we can combine these things together. And the other nice thing is that we experimentally verified this technique in practice. But it's not a rocket science. It cannot replace thinking. It cannot replace the tester. It won't do the work for us because models don't think, it's humans who think. And we use this scientific methods that confirm this result. So yeah, that's all. Thank you very much.
So Adam, thank you very much for your presentation. I think we have a short time for questions from audience. Yes, the first question, please. How do we know when to say stop during test case design? From Krzysztof.
Yeah, of course, we all know the answer. It depends. Well, this is a very general question. In this experiment, the students were told to generate as many test ideas as they were able to. That's because this came from the experimental design. We wanted to check things that were verified through, among others, the number of these test ideas. So in this experiment, of course, the more the better. In real life, the situation, of course, is different. There's a very important notion which is not very well understood, in my opinion, in the software testers world, is the notion of coverage. Because from the formal point of view, we could say we know when to stop during, we know when to say stop designing test cases or test ideas when we reach some threshold of the coverage, which is defined earlier, and this definition of coverage comes from many different factors like risk, like project constraints, like all this kind of stuff. So this always depends on a particular project. But the notion of coverage in terms of this notion is usually used for white box testing, which does not bring much value, in fact. But the general notion of coverage, I think it's quite helpful here.
Thank you. Next question. Is it better to create short test cases and create more of them, or rather create bigger tests which will cover more functionalities?
Well, it again depends. I know one real example in which the testers had to artificially cut, let's say, one nice, simple test case into 24 test cases because the managers told her that 2 test cases, it's not enough, it's a small number. So it's like, you know, in corporations sometimes weird things happen. So of course the test should test what they are intended to test. It always comes from our decision on how to test and what to test and to what degree to test. That always comes from the context. Testing is context dependent, always, always.
Okay, I think the last question. Why there are no cats on the presentation?
Well, I decided to this time to use the Game of Thrones memes or pictures, so sorry. So next time, for the next conference, I will use
obviously.
Cat.
So Adam, thank you very much for your presentation.
Thank you very much.
Ladies and gentlemen, Adam Roman. Thank you.
Thank you.